Hi, my name is Sheraz Choudhary, and I would like to present to you my final project on heart disease prediction and visualization. So first I'll be running through a PowerPoint that will give a quick overview of the project, and then I'll actually go through some of the configurations that I did. So the initial goal of this project is to determine the feasibility of predicting heart disease using a small set of health variables using XGBoost. Then I wanted to take these predictions and the data and via an AWS Big Data Pipeline move the data over to OpenSearch Dashboards where I could do more complicated visualizations and filters. I also discovered this data set was very imbalanced, about 90 to 10 ratio. So I definitely had to deal with that in Python in the data cleanup. Here's the project pipeline. As I mentioned, the dataset is from Kaggle and the link is listed. I then used Python and Jupyter Notebooks to do some data cleanup, balance the data, and finally, after the data was balanced and cleaned, run a fine-tuned XGBoost model to get the best predictions. I'll discuss the predictions later on the next slide. Next, I used Amazon S3 to store the cleaned CSV file. I then used OpenSearch, which is basically an index. It's a way of ingesting data and storing it efficiently. So I created an OpenSearch domain in which I created an index that would host all the fields that are in the data set. I then created an Amazon Kinesis Firehose environment, and this basically allows me to pass data from Amazon S3 via some conversions to Amazon OpenSearch. In order to do the conversion then to pass the data via Kinesis Firehose, I wrote a Python script that was running on Amazon EC2 instance. So the script on the EC2 instance got the data from the S3 bucket. It then piped the data to Amazon Kinesis Firehose as a JSON object, and then Kinesis Firehose put the data into the OpenSearch index that I had set up. Finally, once all the data was in OpenSearch, I used Amazon OpenSearch Dashboards for visualization. As you can see, this is the data set on Kaggle. It was about 25.2 MB, 18 columns, about 320,000 rows, and you can see the 18 columns are listed. This data is originally from the CDC survey that the CDC conducted in 2020, I believe. The data cleanup. So the data was fairly clean. It didn't have any nulls, but there were a lot of categorical variables that could be converted into numerical variables to make it easier for the model to digest the data. In order, as I'll mention, like in the next slide, I'll cover this in more detail, but the data was very unbalanced. So I undersampled the data to balance the variables. I, of course, created train test validation data frames, and then I tuned XGBoost to get the best model accuracy for this particular data set. And then I took the cleaned data and of course piped it into a CSV file, which is what will be transferred over to the Amazon S3 storage for all the later analysis. So as you can see, the data set as it was given had an imbalance of around 91.4% to 8.6%. So if the model were to predict everything was in the dominant class, we'd have an accuracy of 91.4%. The model did 91.9%, which is just slightly better. So the model at least attempted to do some level of prediction rather than just simply predicting the dominant class. But this is not ideal. So I undersampled the data set because we also had to decrease the size anyway. And via undersampling, I got a 50-50 ratio. And you can see the accuracy drops quite a bit. But this is actually more true accuracy versus the imbalanced data set. So you can see the best accuracy we're getting is around 77%, which is pretty good given the simplicity of the health data that we're piping into the model. So as you can see, this is the Amazon S3 bucket. S3 bucket is also where any of the logs, like the failed logs, live. So if anything goes wrong, like there's a failure, it's going to end up in this failed data Amazon OpenSearch failed folder. And you can see I have the original data set, which I won't be using in S3. And then I have the cleaned balanced data set, which is what we'll be using for the rest of the project. So Amazon OpenSearch is, as I mentioned, a way of indexing and handling a lot of big data. So I set up a Amazon OpenSearch domain, and you can see like there are a bunch of links here, and those links are where these links are basically where, you know, like you can access the console and, you know, like other configuration type aspects of OpenSearch. You can see my OpenSearch domain is called health disease domain, and it actually has it's running on 3 R large servers, and I believe it has 13 shards at the moment, and it has a number of indexes on it. So this, like, as I mentioned, like if I click on that link previously to go to the console, this is what the console looks like. And here we have, you know, we can do a bunch of commands, and this is where I'm putting the index, and this index is all the fields that are in the data. OpenSearch is really, really finicky about its data types, to the point where if the Boolean value is true with a capital T, which is the way it would be in Python, it will fail. It will only accept true lowercase and false lowercase. So data has to meet the exact standards of the data type. Even if there's a little bit of variation, it's going to basically fail, and the entry won't be recorded in OpenSearch. So that's something definitely to be mindful of. Like when you're picking the data types, it's very important to know what their specifications are. So as I mentioned, in order to get the data into OpenSearch, I used Amazon Kinesis Firehose. And this Amazon Kinesis Firehose is basically, it's got its destination as the index in OpenSearch. And to Amazon Kinesis Firehose will be passing JSON objects. And this is like when I was doing the run, you can see this is the various statistics for monitoring how the data was being loaded into OpenSearch. This is a portion of the Python script. As you can see, it's on line 52 to 66. This is the portion where it generates a JSON object and then uploads that JSON object to the Kinesis Firehose. And Kinesis Firehose knows once it receives a JSON object to put it into OpenSearch, like that index that I created in OpenSearch. So here you can see, like once we have the data in OpenSearch, we can actually visualize it. So this is all the data. So this dashboard takes a while to construct because it's a fairly manual process of constructing it. But you can see there, I put some filters at the top, and then I have some pie charts showing, you know, the level of whether I got the predictions correct or not, like what the distribution was in the original data. And then I have the age distribution and the health distribution of the data, along with some heat maps that basically map out like whether you have heart disease or not compared to your age, compared to your general health. And then I took the precise predictions from XGBoost and laid them out as a histogram. So of course, XGBoost, when it's like I'm making it pick categories. So the precise predictions aren't, well, like if it's over 0.5, it's going to predict yes. If it's under 0.5, it's going to predict no. But it's still useful to see the distribution of what the probabilities XGBoost assigned to each of the predictions that it made. You can see a BMI distribution. And then basically within this sample, what is the average age, average general health, average diff walking, and average diabetic. Here you can see heart disease yes versus no. So you can see that how the data changes based on yes versus no. Here we can see prediction correct versus incorrect. And once again, we can see how the data moves. Sorry, I jumped ahead one slide, so you can see that this is how the data moves. General health excellent versus poor. And you can see, especially the precise predictions, they move from one end to the other. So general health is definitely something that's being used by the model to make its predictions. Age under 60 versus over 60. And here we can see, like once again, the same type of distribution we saw earlier. So now let me move over to actually going through some of the stuff in a window. So actually showing some of the stuff. So this is the Kaggle data set. And we can see, like all the columns and their distributions. This is so I have two different Jupyter notebooks, one that's unbalanced and one that's balanced. They're identical except for the fact that, one of them balances while the other does not. So we'll go through the balanced one. I load all the libraries, I load the CSV file. I do some data cleanup just to make it easier to ingest by the model. I dropped some columns that, weren't really helping and weren't really needed. So basically the goal of this was just to simplify the data set. Here you can see the EDA of the data. So basically, just some quick describe correlation. So you can see that age category has a pretty significant correlation as well as general health. And we'll see that when we look at the features later on. Here are the types, and you can see they're all ints or floats, which is going to be really easy for our XGBoost model to handle. So I write it to a CSV file here, the cleaned and balanced data set. And then I create a bunch of test, val, and train data frames. This isn't needed for XGBoost, so I chose not to scale the model, scale the data. But if I was running another type of model, I might have to scale the data. So load some machine learning libraries. This is a pair plot. For this particular data, it's not that useful. For some other types of data, you can use it to see some trends that are in the data. So you can actually visually see what data, how the data might be helpful for the model. Import XGBoost, just run it with default parameters, and we get those levels of accuracy. And then do a grid search to optimize the parameters. I actually ran the grid search twice just to try different variables. And you can see this takes a while because it's doing many fits. And these are the parameters it thought were best. Using the max depth of 5 and 50 estimators, I then just had checked every learning rate to see if there was one better than 0.13. And I think at the end, I ended up using 0.1 as the learning rate, which seemed to give more consistent accuracy. So these are the final accuracies for the train, val, and test. Even how similar these are lets me know that regularization won't help, but I gave it a shot anyway. This does not seem like it will profit from regularization. So I ran a grid search for regularization, and it told me 0.5 and 0.7 would be the best values. As you can see, the data is pretty much the same, so I chose to forgo the regularization. I then got the feature importances from XGBoost, which you can see are age category, general health, diff walking, diabetic, stroke. And then we can graph these out so that we can actually see them visually. And you can see age category, general health, diff walking, And so, pretty much here is where you start seeing like a major drop off. So these fields really didn't add much value to the model. BMI especially surprised me because we had a, fairly fine, like it wasn't a 1-0 type of situation. We actually had, like float data on BMIs, but it didn't seem to do that much. And mental health and physical health also didn't do much. I think these were basically how many mental health or physical health instances have you had in the last 30 days. So we can use confusion matrices to visualize how the model did. So these are matrices for training, testing, validation, and all data. And you can see the model is doing a decent job. It's slightly over-predicting that people would have a heart disease. So, given that we know our model is 50-50, if this added up was exactly the same as this added up, that would show that the model did a fairly good job. Here we can tell the model skewing slightly towards predicting that health disease is there when it actually might not be, which is why it actually made a mistake of 7,200 for predicting yes while the real answer was no. Predicting no while the real answer was yes was only around 5,000. So I take these probabilities. Here you can see the precise probability that I mentioned earlier versus the predicted probability. And I took these and I added them to the original balanced data set. So this is basically just concatenating them together. And then I saved that CSV file as well. So this CSV file has the cleaned columns plus a prediction, precise prediction, and whether it was correct or not columns. This was the file that I stored in Amazon AWS S3. As I mentioned, here's where the failed logs live. And this is basically my Amazon OpenSearch service domain. One of the things that to be careful of, so you can see the cluster configuration here. It's basically 3 R5 large search instances on Amazon. I'm only running it in one availability zone because, this is not a production environment, so we don't need multiple availability zones. And I don't even have a master node because, once again, this is not a production environment, so there's no need for a master node. One thing to be careful of, which took me a while to figure out, if I go to edit, you can see down here, where is it? Under advanced options, I believe. Nope. Pardon me, I'm trying to find where one of the things that caused me a lot of grief were. If I don't find it soon, I'm just going to skip ahead, but I'm going to cancel this. I had a checkbox which was preventing me from loading data into OpenSearch. And once I checked the checkbox again, then data loaded appropriately. But the error was present in the logs, which is how I figured out what was happening. So you can see security configuration, cluster health, all kinds of, data that would be useful in a production environment. So we're going to skip over most of these. So next, this is where we created the indexes. So you can see if I click over here and say, show me the indexes, you can see we have a heart disease index and a Kibana _1 index, which is basically just a default index that's always there. So this is the index that I added. And you can see if I want to look at the data, you can see 10,000 values were returned, and you can see this is the first entry. This is the second entry. So it limits the return to 10,000, so you actually can't tell how many actual rows there are in the index. So this command lets you see that there are 52,951 rows in here. So that's how we use the console. And this is basically how you create the index. And these mappings are really important, especially if there was a categorical variable. I would recommend not using string or text, but rather using keyword, because if you use text, there's really no analysis you can do on that. So that field basically is not really useful for a dashboard or anything like that. Here's my Amazon Kinesis Firehose, and you can see, so this is basically what I'm using to pass data to OpenSearch from the CSV file. You can see that this is how the run occurred, the one that I showed earlier in the slides. As you can see, there were multiple attempts because this is where I ended up with some errors, so I had to redo the run. Here's the configuration. The index I'm sending it to is heart disease, which I mentioned earlier. So the index has to be created before so you can specify the index here. The S3 bucket is where I'm going to put all the logs, the failure logs. And I also have CloudWatch logs enabled so that I can get further information as to why stuff failed. And the AIM role is over here. And as you can see, I added full access to OpenSearch service for the role, just so that everything worked as desired in OpenSearch. More granular permissions might be required if it's a production environment. So this is my Amazon EC2 instance. Here, let me click that again. So you can see this is a fairly large M5 extra large instance. Probably overkill for this particular purpose, because I probably could have even done with a large or even a medium. But you can see the security. The security basically allows only connections from my IP address, the way it's set up right now. So anything coming from my IP address is allowed, but everything else is not. So that's pretty much all the configuration we need for the EC2 instance. Once you have this checked, you can click connect. And if you go to SSH, you can get the command to connect to the EC2 instance from the command line. So as I mentioned, this is the Python script. So I import a bunch of libraries along with Boto3 is a Amazon library. And AWS Kinesis is going to be Boto3 client for Firehose, and S3 Connect will be Boto client for S3 buckets. So you can see I specify the columns in the data set, and then I go to the file in S3 and I connect to it, and I basically get the CSV file. And then I upload it. I removed the header, so sometimes the files don't have headers, so I didn't want to rely on it having a header. And I said the names of the columns are the names specified up here. So that basically gets the file from S3. And over here, I'm taking this is a for loop. For each row, I'm getting all the fields. And then I'm creating a JSON document from those fields. And then I remove any entries that have null values. Our data set didn't have nulls, but better to be careful so that there aren't any errors. And then it sends this JSON object to the Kinesis data stream. So you can see like we are sending it to the put heart data Kinesis data stream that we created. And you can see it's putting that JSON object in there. So this is basically set up for the EC2 instance. This EC2 instance here is once I connected to the instance. So here is basically where I connect to the instance. And I'm going to install a bunch of libraries. You also have to do AWS configure. Of course, I've hidden my AWS access and secret keys. And the region I'm working in is US East 1. So these are basically installs, installing Boto3, installing pip, installing NumPy, installing pandas, installing requests. This is where I wrote the Python script using Nano, and this is where I run the Python script. And you can see I ran it a few times because of the errors that I encountered, as I mentioned before. But once you run the script, it basically will take about 10 to 15 minutes to upload all the data. And that's basically all that happened here. And you can see that the CSV file is now sitting on the server because we got it using the script. CloudWatch is where there'll be information if other types, some failures end up in the S3 bucket, other types of failures end up in CloudWatch. So this is a place to go if things failed during the transfer. So you can see this is the S3 bucket and this is the failed folder, and it's basically date based. And you can see here are the error logs. So this is, as I mentioned, initially there was a failure as a result of some configuration, but here you can see failed to parse value true as only true or false. So OpenSearch can't even understand that true with a capital T is the same as true with a all lowercase. So it will legit do no conversions for you. So it won't try to save you. If it doesn't have the data the way it wants it, it's not going to convert it. It's just going to fail out. So you can see like this is many failures, which is basically for all the rows that were in the data set. So this is Amazon OpenSearch, and here you can see a heart disease index. This is the index that I created. Total size of 16.6 MB, nearly 53,000 records in there. Here are the mappings that I specified. I don't believe there is an alias for it. No, there isn't. So, and you can see this is the default index, which is fairly small. So this is the index that we'll be using. And we can also go into, there's all this kind of, you go to DevTools, you end up at the console. There's another place that might be useful, OpenSearch Dashboards Overview. And this is basically where you would set up index management, I believe is, so this is where you want to create policies for your indexes. So before you can use Amazon OpenSearch Dashboards, you have to first create a index policy so that you can visualize the data in OpenSearch. So this is OpenSearch, and if I click edit, you can see these things, but it's fairly tedious to create stuff. But like you have area controls of those filters, they're experimental. But let's say we want to, I'll actually just duplicate one of these right now to make it a little easier. So if I clone this panel and I click on edit visualization, here you can see how it's actually done. So I selected histogram as the aggregation. Usually you'd be selecting terms if you don't want a histogram. And the field I want is BMI. I can set the field to anything. Like if I wanted to switch this to precise predictions, I could do that and click update, and you'll see there the precise predictions. But this was at BMI originally. You can also add a y-axis. So this is basically how you would go about creating each of those panels that you saw in the dashboard. So I'll say cancel to this, confirm, and I'll delete this extra panel that I created. So here we go. We can save this to go back to the way it was. So outside of edit mode. And here you can see like this is where I can say heart disease, yes, apply changes, and you'll see all the data shifts. And you can see a filter's been added up here. So if I want to get rid of it, I can just clear that. And now we end up with all the data. So this is basically how OpenSearch dashboards work. They're extremely fast because they're working on index data. I love these heat maps. You can go in and edit this, where if I wanted to change something inside it, for example, we can take the y-axis, and right now it's 20. I can set it to 10, and you'll see like it removed some of the entries. I know that I only have about 15 age ranges, so setting it to 20 ensures that I get them all. I can sort them ascending or descending. We'll stick with ascending, which makes a lot more sense to me. But you can see, like, for heart disease, a lot of heart disease in 82-year-olds. For some reason, 77-year-olds don't have as much heart disease, but then 72-year-olds also have a lot of heart disease. So age is definitely a major component of heart disease, because you can see over here, practically no heart disease up till the age of 52 or so. 57 is where you start seeing heart disease, and 62 is where you really see an increase in the amount of heart disease. So this is basically how, I ran my project. Now that this particular dashboard is created, you can run all kinds of combinations. So you can say heart disease, yes. We'll say it's in actually a younger population, and we'll say general health is excellent. There shouldn't be that many people that have heart disease with these criteria. So you can see there are 100% of these people have heart disease because we put that as a filter. But our model only predicted 14.8% of these people would have a heart disease because, of course, this isn't the group we would expect to have heart disease. So you can dig into these things as to why the model predicted that these 14% would have, or why these 85% would not have. So you can do all these various filters and see like what's actually happening when you combine different filters. So here you can see we only have a few values with all three of these filters enabled. But you can see like the model got nearly all of them wrong because this is an age group and a health group that you wouldn't expect to have heart disease. So yeah, that's pretty much it. If there are any questions, feel free to get in touch with me. But this was a fun project to work on. The AWS Big Data Pipeline took a lot of time. So just getting data to this dashboard is a heavy lift. But after it's here, it actually works wonderfully. And you can see it's extremely powerful for doing analysis. And this is the first time that I've brought in the precise predictions into the data, into the dashboard. And I do find the value in being able to see what the model was thinking for each of those combinations. With that, thank you for your time.